a WikiVidi documentaries production. Don't forget to like and subscribe. Enjoy. Tunnel. A tunnel is an underground passageway, dug through the surrounding soil/earth/rock and enclosed except for entrance and exit, commonly at each end. A pipeline is not a tunnel. Though some recent tunnels have used immersed tube construction techniques rather than traditional tunnel boring methods. A tunnel may be for foot or vehicular road traffic, for rail traffic, or for a canal. The central portions of a rapid transit network are usually in tunnel. Some tunnels are aqueducts to supply water for consumption or for hydroelectric stations or are sewers. Utility tunnels are used for routing steam, chilled water, electrical power or telecommunication cables, as well as connecting buildings for convenient passage of people and equipment. Secret tunnels are built for military purposes or by civilians for smuggling of weapons, contraband, or people. Special tunnels, such as wildlife crossings, are built to allow wildlife to cross human-made barriers safely. Tunnels can be connected together in tunnel networks. Terminology. A tunnel is relatively long and narrow. The length is often much greater than twice the diameter, although similar shorter excavations can be constructed, such as cross passages between tunnels. The definition of what constitutes a tunnel can vary widely from source to source. For example, the definition of a road tunnel in the United Kingdom is defined as a subsurface highway structure enclosed for a length of 150 meters or more. In the United States, the NFPA definition of a tunnel is an underground structure with a design length greater than 23 meters and a diameter greater than 1,800 millimeters. In the UK, a pedestrian, cycle or animal tunnel beneath a road or railway is called a subway, while an underground railway system is differently named in different cities: the Underground or the Tube in London, the Subway in Glasgow, and the Metro in Newcastle. The place where a road, railway, canal or watercourse passes under a footpath, cycleway, or another road or railway is most commonly called a bridge or, if passing under a canal, an aqueduct. Where it is important to stress that it is passing underneath, it may be called an underpass, though the official term when passing under a railway is an underbridge. A longer underpass containing a road, canal, or railway is normally called a tunnel, whether or not it passes under another item of infrastructure. An underpass of any length under a river is also usually called a tunnel, whatever mode of transport it is for. In the US, the term subway means an underground rapid transit system, and the term pedestrian underpass is used for a passage beneath a barrier. Rail station platforms may be connected by pedestrian tunnels or footbridges. Geotechnical investigation and design. A major tunnel project must start with a comprehensive investigation of ground conditions by collecting samples from boreholes and by other geophysical techniques. An informed choice can then be made of machinery and methods for excavation and ground support, which will reduce the risk of encountering unforeseen ground conditions. In planning the route, the horizontal and vertical alignments can be selected to make use of the best ground and water conditions. It is common practice to locate a tunnel deeper than otherwise would be required, in order to excavate through solid rock or other material that is easier to support during construction. Conventional desk and preliminary site studies may yield insufficient information to assess such factors as the blocky nature of rocks, the exact location of fault zones, or the stand-up times of softer ground. This may be a particular concern in large-diameter tunnels. To give more information, a pilot tunnel may be driven ahead of the main excavation. This smaller tunnel is less likely to collapse catastrophically should unexpected conditions be met, and it can be incorporated into the final tunnel or used as a backup or emergency escape passage. Alternatively, horizontal boreholes may sometimes be drilled ahead of the advancing tunnel face. Other key geotechnical factors. Choice of tunnels versus bridges. For water crossings, a tunnel is generally more costly to construct than a bridge. However, navigational considerations may limit the use of higher bridges or drawbridge spans intersecting with shipping channels, necessitating a tunnel. Bridges usually require a larger footprint on each shore than tunnels. In areas with expensive real estate, such as Manhattan and urban Hong Kong, this is a strong factor in favor of a tunnel. Boston's Big Dig project replaced elevated roadways with a tunnel system to increase traffic capacity, hide traffic, reclaim land, redecorate, and reunite the city with the waterfront. The 1934 Queensway Tunnel under the River Mersey at Liverpool was chosen over a massively high bridge for defence reasons. It was feared that aircraft could destroy a bridge in times of war. Maintenance costs of a massive bridge to allow the world's largest ships to navigate under were considered higher than for a tunnel. Similar conclusions were reached for the 1971 Kingsway Tunnel under the Mersey. In Hampton Roads, Virginia, tunnels were chosen over bridges for strategic considerations. In the event of damage, bridges would prevent U.S. Navy vessels from leaving Naval Station Norfolk. Water-crossing tunnels built instead of bridges include the Holland Tunnel and Lincoln Tunnel between New Jersey and Manhattan in New York City, the Queens Midtown Tunnel between Manhattan and the Borough of Queens on Long Island, the Detroit-Windsor Tunnel between Michigan and Ontario, and the Elizabeth River Tunnels between Norfolk and Portsmouth, Virginia, the 1934 River Mersey Road Queensway Tunnel, the Western Scheldt Tunnel, Zeeland, Netherlands, and the North Shore Connector Tunnel in Pittsburgh, Pennsylvania. Other reasons for choosing a tunnel instead of a bridge include avoiding difficulties with tides, weather, and shipping during construction, aesthetic reasons, and also for weight capacity reasons. Some water crossings are a mixture of bridges and tunnels, such as the Denmark to Sweden link and the Chesapeake Bay Bridge Tunnel in Virginia. There are particular hazards with tunnels, especially from vehicle fires when combustion gases can asphyxiate users, as happened at the Gotthard Road Tunnel in Switzerland in 2001. One of the worst railway disasters ever, the Balvano train disaster, was caused by a train stalling in the Army Tunnel in Italy in 1944, killing 426 passengers. Designers try to reduce these risks by installing emergency ventilation systems or isolated emergency escape tunnels parallel to the main passage. Project planning and cost estimates. Government funds are often required for the creation of tunnels. When a tunnel is being planned or constructed, economics and politics play a large factor in the decision-making process. Civil engineers usually use project management techniques for developing a major structure. Understanding the amount of time the project requires, and the amount of labor and materials needed is a crucial part of project planning. The project duration must be identified using a work breakdown structure and critical path method. Also, the land needed for excavation and construction staging and the proper machinery must be selected. Large infrastructure projects require millions or even billions of dollars, involving long-term financing, usually through issuance of bonds. The costs and benefits for an infrastructure such as a tunnel must be identified. Political disputes can occur, as in 2005 when the U.S. House of Representatives approved a $100 million federal grant to build a tunnel under New York Harbor. However, the Port Authority of New York and New Jersey was not aware of this bill and had not asked for a grant for such a project. Increased taxes to finance a large project may cause opposition. Construction. Tunnels are dug in types of materials varying from soft clay to hard rock. The method of tunnel construction depends on such factors as the ground conditions, the groundwater conditions, the length and diameter of the tunnel drive, the depth of the tunnel, the logistics of supporting the tunnel excavation, the final use and shape of the tunnel, and appropriate risk management. There are three basic types of tunnel construction in common use. Cut-and-cover tunnels are constructed in a shallow trench and then covered over. Bored tunnels are constructed in situ, without removing the ground above. Finally, a tube can be sunk into a body of water, which is called an immersed tunnel. Cut-and-cover. Cut-and-cover is a simple method of construction for shallow tunnels where a trench is excavated and roofed over with an overhead support system strong enough to carry the load of what is to be built above the tunnel. Two basic forms of cut-and-cover tunneling are available. Shallow tunnels are often of the cut-and-cover type, while deep tunnels are excavated, often using a tunneling shield. For intermediate levels, both methods are possible. Large cut-and-cover boxes are often used for underground metro stations, such as Canary Wharf Tube Station in London. This construction form generally has two levels, which allows economical arrangements for ticket hall, station platforms, passenger access and emergency egress, ventilation and smoke control, staff rooms, and equipment rooms. The interior of Canary Wharf Station has been likened to an underground cathedral, owing to the sheer size of the excavation. This contrasts with many traditional stations on London Underground, where bored tunnels were used for stations and passenger access. Nevertheless, the original parts of the London Underground network, the Metropolitan and District Railways, were constructed using cut-and-cover. These lines predated electric traction, and the proximity to the surface was useful to ventilate the inevitable smoke and steam. A major disadvantage of cut-and-cover is the widespread disruption generated at the surface level during construction. This, and the availability of electric traction, brought about London Underground switch to bored tunnels at a deeper level towards the end of the 19th century. Boring machines. Tunnel boring machines and associated backup systems are used to highly automate the entire tunneling process, reducing tunneling costs. In certain predominantly urban applications, tunnel boring is viewed as quick and cost-effective alternative to laying surface rails and roads. Expensive compulsory purchase of buildings and land, with potentially lengthy planning inquiries, is eliminated. Disadvantages of TBMs arise from their usually large size, the difficulty of transporting the large TBM to the site of tunnel construction, or the high cost of assembling the TBM on site, often within the confines of the tunnel being constructed. There are a variety of TBM designs that can operate in a variety of conditions, from hard rock to soft water-bearing ground. Some types of TBMs, the bentonite slurry and earth pressure balance machines, have pressurized compartments at the front end, allowing them to be used in difficult conditions below the water table. This pressurizes the ground ahead of the TBM, cut ahead to balance the water pressure. The operators work in normal air pressure behind the pressurized compartment, but may occasionally have to enter that compartment to renew or repair the cutters. This requires special precautions, such as local ground treatment or halting the TBM at a position free from water. Despite these difficulties, TBMs are now preferred over the older method of tunneling in compressed air, with an airlock/decompression chamber some way back from the TBM, which required operators to work in high pressure and go through decompression procedures at the end of their shifts, much like deep-sea divers. In February 2010, WikiVidi delivered a TBM to Switzerland for the expansion of the Linthlimmen power stations located south of Linthal in the canton of Gleus. The borehole has a diameter of 8.03 meters. The 4 TBMs used for excavating the 57 km Gotthard base tunnel in Switzerland had a diameter of about 9 meters. A larger TBM was built to bore the Greenhart Tunnel as part of the HS Elzert in the Netherlands, with a diameter of 14.87 meters. This in turn was superseded by the Madrid M30 ring road, Spain, and the Chongming tunnels in Shanghai, China. All of these machines were built at least partly by Herrenlicht. The world's largest TBM is Big Bertha, a 57.5 feet diameter machine built by Hitachi Zosen Corporation, which is digging the Alaskan Way Viaduct Replacement Tunnel in Seattle, Washington. Clay kicking. Clay kicking is a specialized method developed in the United Kingdom of digging tunnels in strong clay-based soil structures. Unlike previous manual methods of using mattocks which relied on the soil structure to be hard, clay kicking was relatively silent and hence did not harm soft clay-based structures. The clay kicker lies on a plank at a 45-degree angle away from the working face and inserts a tool with a cup-like rounded end with the feet. Turning the tool manually, the kicker extracts a section of soil, which is then placed on the waste extract, used in Victorian civil engineering. The method found favour in the renewal of Britain's ancient sewerage systems, by not having to remove all property or infrastructure to create a small tunnel system. During the First World War, the system was used by Royal Engineer tunnelling companies to put mines beneath the German Empire lines. The method was virtually silent and so not susceptible to listening methods of detection. Shafts. A temporary access shaft is sometimes necessary during the excavation of a tunnel. They are usually circular and go straight down until they reach the level at which the tunnel is going to be built. A shaft normally has concrete walls and is usually built to be permanent. Once the access shafts are complete, TBMs are lowered to the bottom and excavation can start. Shafts are the main entrance in and out of the tunnel until the project is completed. If a tunnel is going to be long, multiple shafts at various locations may be bored so that entrance to the tunnel is closer to the unexcavated area. Once construction is complete, construction access shafts are often used as ventilation shafts, and may also be used as emergency exits. Sprayed concrete techniques. The new Austrian tunneling method was developed in the 1960s and is the best known of a number of engineering practices that use calculated and empirical measurements to provide safe support to the tunnel lining. The main idea of this method is to use the geological stress of the surrounding rock mass to stabilize the tunnel, by allowing a measured relaxation and stress reassignment into the surrounding rock to prevent full loads becoming imposed on the supports. Based on geotechnical measurements, an optimal cross-section is computed. The excavation is protected by a layer of sprayed concrete, commonly referred to as shotcrete. Other support measures can include steel arches, rock bolts and mesh. Technological developments in sprayed concrete technology have resulted in steel and polypropylene fibers being added to the concrete mix to improve lining strength. This creates a natural load-bearing ring, which minimizes the rock's deformation. By special monitoring, the NAT method is flexible, even at surprising changes of the geomechanical rock consistency during the tunneling work. The measured rock properties lead to appropriate tools for tunnel strengthening. In the last decades also soft ground excavations up to 10 kilometers became usual. Pipe jacking. In pipe jacking, hydraulic jacks are used to push specially made pipes through the ground behind a TBM or shield. This method is commonly used to create tunnels under existing structures, such as roads or railways. Tunnels constructed by pipe jacking are normally small diameter bores with a maximum size of around 3.2 meters. Box jacking. Box jacking is similar to pipe jacking, but instead of jacking tubes, a box-shaped tunnel is used. Jacked boxes can be a much larger span than a pipe jack, with the span of some box jacks in excess of 20 meters. A cutting head is normally used at the front of the box being jacked, and spoil removal is normally by excavator from within the box. Recent developments of the jacked arch and jacked deck have enabled longer and larger structures to be installed to close accuracy. The 126 meters long 20 meters clear span underpass below the high-speed rail lines at Cliffsend in Kent, UK is an example of this technique. Brought to you by WikiVidi documentaries. Would you like to know more?